In our lesson today, we're going to look at proportional and non-proportional relationships through tables. And what we're going to do in our first example is look at the relationship between the side length of a square and the perimeter of a square. The diagram shows a series of squares drawn on graph paper. The side length and perimeter of each square are labeled. Use the diagram to complete the table. Draw the next few squares as needed. Write all ratios in simplest form. So for the first three squares, again, we can see S, which stands for the side length, and P, which is the perimeter. Okay, the way that you get the perimeter of a square is by multiplying the side length by 4. Okay, so 1 times 4 is 4. If the side length is 2, 2 times 4 gives you a perimeter of 8. If the side length was 3, 3 times 4 gives a perimeter of 12, and so on. So let's take a look at our table and see if we can fill in the missing spots. The first side length was equal to 1, and its perimeter was equal to 4. Underneath of that, in the empty box, we're going to write a ratio of perimeter over side length. So for this square, the perimeter was 4, and the side length was 1. Now, they said write all ratios in simplest form. 4 over 1 is already in simplest form. So let's move on to the next square where the side length was equal to 2. Okay, well, that was this square right here. When the side length was 2, we multiplied that by 4 to get a perimeter of 8. Underneath of that, they set up the ratio of perimeter over side length as 8 over 2, and that simplifies down to 4 over 1. You can divide 8 and 2 both by 2, which gives you 4 over 1. The next side length we're going to look at is a side length of 3, which is this square right here. If we take the side length of 3 and multiply it by 4, that gave us a perimeter of 12. And so let's write the ratio of perimeter over side length. The perimeter was 12. The side length was 3. 12 over 3, both of those numbers, if you divide by 3, would simplify down to 4 over 1. In the next example, they gave us a square that has a perimeter of 16. The side length for that square then must be 4 because 4 times 4 equals 16. For the ratio of perimeter over side length, we're going to have 16 over 4. Both of those numbers divided by 4 would give you 4 over 1 in simplest form. The next one is a side length of 5. If you do the side length times 4, that would give you the perimeter. So 5 times 4 is 20. For the ratio of perimeter to side length, that's going to be 20 over 5. Both of those numbers you can divide by 5, which would give you 4 over 1. Finally, they gave us a square with a perimeter of 24. What number times 4 is 24? Well, that must mean the side length is 6 because 6 times 4 is 24. For the ratio of perimeter to side length, that's going to be 24 over 6. Both of those numbers divided by 6 would give us 4 over 1 in simplest form. And so underneath, they've asked us the question, what do you notice about the ratio of perimeter to side length for each square? Well, if I look at all of the ratios in this row here, they all were equal to 4 over 1. So let's write that in. All of the ratios are equivalent. All of the ratios are equivalent. They all simplify to 4 over 1. So all of the ratios of perimeter to side length in this example are equivalent. So let's take a look at the next diagram. Again, we have a series of squares. This time, the side length and the area of the square are labeled. So we have a side length of 1 and an area of 1, a side length of 2 and an area of 4, a side length of 3 and an area of 9. The way that you get the area of a square is by multiplying the side length by itself. So in our first square, 1 times 1 equals 1, which is how we got that area. Side length of 2, 2 times 2 equals 4, which is how we got that area right there. Side length of 3. 3 times 3 equals 9, which is how we got that area right there. So you do the side length times itself to get the area. This time in our chart, we have the side length, the area, and we're going to do area over side length. So for our first square, the side length was 1, the area was 1. That ratio is going to be 1 over 1, which was already in simplest form. For our second square, with the side length of 2, that gave us an area of 4. 2 times 2 is 4. The ratio this time, area over side length, is 4 over 2, which is equal to 2 over 1. In our next example, the side length is 3, which is that square right there. 3 times 3 gave us an area of 9. When we do area over side length this time, we're going to get 9 over 3, which simplifies down to 3 over 1. If we had an area of 16, what number times itself equals 16? Well, that would be 4. 4 times 4 is 16. Area over side length is going to be 16 over 4, which will simplify down to 4 over 1. If the side length was 5, 5 times 5 would give an area of 25. Area over side length is 25 over 5, which simplifies down to 5 over 1. And finally, they gave us a square with an area of 36. What number times itself is 36? Well, that's 6 times 6 was 36. So the area over side length here is 36 over 6, which in this case simplifies down to 6 over 1. So this time, what do you notice about the ratio of area to side length for each square? Well, when we did perimeter to side length, all of the ratios were equivalent, but when we did area to side length, we see that the ratios are not equivalent. Let's write that down. The ratios are not equivalent. Okay, so these two examples are going to help us understand what it means for a relationship to be proportional and what it means for a relationship to be non-proportional. So in our little box here, we're going to tell what it means for a relationship to be proportional and what it means for a relationship to be non-proportional. A proportional relationship between two quantities means that they have a constant unit rate. Okay, so what does that mean? Well, that means that all rates are equal. And so from the front page, which relationship shows a proportional relationship? Well, if we go back and look, we had in this example right here, when we were looking at perimeter to side length, all of the ratios were equal to each other. So that represents a proportional relationship. So we're going to say that perimeter to side length represents a proportional relationship, again, because all of the ratios there were equivalent to 4 over 1. Non-proportional relationship between two quantities means that they do not have a constant unit rate. Okay, and so that means that all rates are not equal. Okay, you might get some rates that are equal, but if not all of them are equal, then you're going to have a non-proportional relationship. So from the front page, which relationship shows a non-proportional relationship? Well, looking back, it was this one down here at the bottom. Okay, if we look at all of these ratios, none of them, when we simplified, were equal to each other. This was area to side length. So let's go ahead and write that in from the front page. It was area to side length that was a non-proportional relationship. Okay, and then equivalent ratios are ratios with the same value. Okay, for example, on the front, when we were simplifying 8 over 2, that is equal to 4 over 1. Those two ratios are equivalent to each other. In the next example, we're going to try to determine if there is a proportional or a non-proportional relationship between the two quantities. Mrs. Cochran is planning a pizza party for her students. Ace Pizza offers free delivery and charges $8 per medium pizza. Complete the table to determine the cost for ordering different number of pizzas ordered. Okay, so they told us right there it's $8 per pizza. So we can see in the first set, we've got one pizza costs $8, which means two pizzas will cost $16. 3 pizzas will be $24. 4 pizzas will be $32, and 5 pizzas will be $40. So there's our table. And now what we're going to do is compare these two quantities and see if there is a proportional relationship. Our rate is going to compare the cost per pizza. All right, so we're going to put the dollars over the number of pizzas ordered. And I've done the first one for you. We can see from the table that it costs $8 for one pizza. What we're going to want to do with all of our ratios is simplify them. 8 over 1 is already written in simplest form. So I'm going to move on to the next example. All right, for the second set of data from our table, we can see that it costs $16 for 2 pizzas. We can divide both of those numbers by 2, which is going to give us 8 over 1 in simplest form. With the third set of data from our table, it costs $24 for 3 pizzas. Both numbers there can be divided by 3, which is going to give us 8 over 1 in simplest form. The fourth set of data says that it was $32 for 4 pizzas. And again, I can divide both of those numbers by 4, which is going to give me in simplest form 8 over 1. And finally, my last set of data shows that it was $40 for 5 pizzas. I can simplify that down, divide both numbers by 5, 8 over 1 in simplest form. Okay, so for part B, it says, what do you notice about the simplified ratios? Well, looking at all of my ratios, I can see that they are equivalent. All of the ratios simplified down to 8 over 1. Since they were all equivalent, this means that the cost to pizzas ordered is a proportional relationship. Okay, this is a proportional relationship. Every ratio simplified down to 8 over 1, which means that there is a constant unit rate. So let's write that in. There is a constant unit rate of, and now if we investigate 8 over 1, 8 was the amount of dollars for one pizza, so the constant unit rate was $8 per pizza. There is a constant unit rate of $8 per pizza, and again, this was a proportional relationship. In example 2, we're told that Uptown Tickets charges $7 per baseball game ticket plus a $3 processing fee per order. Is the cost of an order proportional to the number of tickets ordered? So again, we're going to use our data from the table and we're going to set up our rates. So we're going to set them up as dollars per ticket. So dollars over tickets. Go ahead and write that in there. And now we're going to look at all of our data. So from the first set of data in our table, the cost was $10, and that was for one ticket. 10 over 1 is already in simplest form. All right, so I'm going to go ahead and move on to my next set of data where I can see the cost was $17 for 2 tickets. Now, I need to figure out what the cost is for 1 ticket, so I'm going to have to divide both of these numbers by 2. And so if I do 17 divided by 2, that's going to give me a decimal of 8 5/10. But remember, we're dealing with money here, which means that's going to be $8.50 per ticket. If I look at the third set of data, I can see that it costs $24 for 3 tickets. Again, I'm looking for the cost of just 1 ticket, so I would divide by 3. 24 divided by 3 means that it's going to be $8 per ticket. And then finally, I'm going to have $31 for 4 tickets. To get the cost of just 1 ticket, I'm going to have to divide both of the numbers by 4. 31 divided by 4, well, that's going to be 7 75/100ths, which means that it's $7.75 per ticket. Look at the 4 unit rates this time. 10 over 1, 850 over 1, 8 over 1, 775 over 1. The ratios of costs to tickets are not equivalent. Okay, they are not equal to each other. Therefore, this shows a non-proportional relationship. Okay, remember, for the relationship to be proportional, all of the unit rates would have to be equal to each other. In this example, none of them are. In our next example, they want to know which situation represents a proportional relationship between the hours worked and the amount earned for Matt and Jane. And so we can see 2 different tables. On top, we have the information for Matt. We can see how much he earned for the number of hours that he worked. And then underneath, we have the same data for Jane, the amount that she earned and how many hours she worked. We're going to try to figure out whose relationship represents a proportional relationship. And the rate that we're going to look for is the dollars per hour. So we're going to do dollars over hours when we set up all of our rates. So let's start with Matt. His first set of data shows that he earned $12 for working 1 hour. That's already in simplest form. So I'm going to move on to the next set of data where I could see that he earned $20 for working 2 hours. Both of those numbers can be divided by 2, which is going to be equal to $10 for 1 hour. And then we have, in the last example, $31 earned for 3 hours. All right, if I divide each of these numbers by 3 to get to that unit rate here, 31 divided by 3 is going to be 10 3/10 repeated. If you punch that into your calculator, you'll see 3, 3, 3, 3, 3, 3, 3, on and on forever. So these are the 3 unit rates for Matt: 12 over 1, 10 over 1, 10 3/10 repeated over 1. Now let's do the same thing for Jane. So here's Jane's information. Again, we're setting this up as dollars over hours. Make sure that you write that on your paper. For Jane, for her first set of data, she earned $12 for working 1 hour. 12 over 1 is in simplest form. Next, she earned $24 for working 2 hours. If I divide both of these numbers by 2, well, then that's going to give me a unit rate of 12 over 1. And then she earned $36 for working 3 hours. To get the amount earned for 1 hour, I'm going to have to divide by 3. 36 divided by 3 is equal to 12. So again, we get 12 over 1. So Jane was 12 over 1, 12 over 1, 12 over 1 when you look at the 3 unit rates. So whose situation represents a proportional relationship, Matt or Jane? Well, Matt, his unit rates were not equivalent, but Jane's were. So it's going to be for Jane. Okay, and we're going to explain why. For Jane, the ratios are all equivalent. There is a constant unit rate of $12 per hour. When we simplified each one of those rates down, we got 12 over 1, which in this case means $12 per hour. So since Jane's unit rates were all equivalent, her relationship is proportional. Since Matt's unit rates were not equivalent, his relationship would be called non-proportional.